Today we're going to be discussing lessons 4 and 5. So lesson 4 is on percent yield. Essentially this relates to the error that comes every time you do a lab. Calculated results are very rarely going to be the same as the results contained or obtained from lab just because of all the sources of error you can have. So the theoretical yield is essentially what you would calculate, what you think you should get, whereas the actual yield is what you're going to actually get in lab. The percent yield is essentially going to be a ratio of those two, so the actual yield to the theoretical yield times 100. So this, we're going to go through a practice problem, but this is more straightforward than a lot of the other stuff we've been doing, except some of it does involve these types of calculations. So the first thing, again, make sure you have balanced reactions. So if we have Na of Cl2 forming NaCl, we're going to need a 2 here and a 2 there, so it's balanced, okay? Then after that, we need to figure out the theoretical yield. So Ty, the theoretical yield, we're going to have to do a calculation. So we're starting with 17 grams of sodium. We want to figure out, through some calculations, what should we get? How much of this should we get in lab? So if we take 17 grams of Na, we need the molar mass of sodium, which if you look at the periodic table, it's just the number for sodium, which should be 22.99 grams. That's the number of grams in a mole. And we need to get to, ultimately, grams of this. So we want to use our mole ratio, so we have 2 moles Na to 2 moles NaCl. And that's from these numbers here. Then we need to get to grams of NaCl. So Na plus Cl, when you use the periodic table to figure that out, it should be around 58.44 grams NaCl. And that's in 1 mole. So when you go ahead and multiply across the top, divide by everything on the bottom, you're going to get 43.21 grams of NaCl. Now, it says that in lab you got 40 grams of sodium chloride, okay? So to find the percent yield, you're going to take the actual, what you actually got in lab, which is the 40 grams. Divide that by the theoretical, which is what we calculated. Multiply by 100 because it's a percent, so grams will cancel. Once you go ahead and calculate that out, make sure it's a percent, you're going to get 92.6. Which means that it was a pretty good turnout in your experiment. You got 92% of what you thought you should get, which is pretty good overall. Alright, so there's plenty other practice problems, but that's essentially how you do these. You need to first make sure it's balanced, figure out your theoretical, use your actual, take a ratio, and get the percent. Okay? Now, lesson 5, we're going to talk about just kind of quickly some reactions in real life that are going to involve stoichiometry, how you can kind of use this stuff in everyday life. So first of all, it's using airbag design. So essentially in airbag designs, you're going to have to make sure you know how much product you're going to form to get the right kind of pressure in the airbag so it's not too strong, it's not too weak, and it can do its job. So here's some reactions, but you can essentially use these reactions to do some calculations, such as this. So assuming that you needed this much of gas to inflate an airbag to the proper size, you can go ahead and work out how much in reactants you would need to do this. Water from camel, so essentially some animals are going to have a lot of different reactions going on in their body that this stuff can be useful. So if you want to know how much water can be produced, you can kind of go through this type of calculation as well. Rocket fuel, figuring out how much rocket fuel you need to make it a certain distance if you're doing any space calculations. We have water in space calculations, something similar. So you need to have some water in space, depending on what you're using for space travel. If you need any water produced, you want to try to get the water. You also don't want to have a lot of other excess reactants aboard a ship if we're talking about space travel again. So here's another example. So essentially you wanted the lithium hydroxide scrubber to remove excess carbon dioxide, which can be harmful to humans. We eventually want oxygen to breathe in. In the pharmaceutical drug industry, essentially you want to make sure you have the right amount of the active ingredient. It needs to be effective. Too much can be deadly, but if you have too much of it, it also is going to cost the company more. So you kind of want to work on the right amount. And in food chemistry, so this can be as simple as if you add too much baking soda, the food's going to be bitter tasting. You want to calculate the right amount. Or if you don't add eggs, baked items will not rise. Those kinds of things too. And it can get much more complex. This is the job of food chemists. They do some sort of quality control calculations. Here's a scenario. Basically, if you were a NASA engineer, you want to make sure you have enough oxygen, not carbon dioxide on the ship, so that you can make sure we're breathing in the proper gases to keep our bodies alive. So this stuff is going to be really important. You can come look at this later when we start talking about our project, but there's just some quick applications of this stuff in everyday life. Also, just so you know, tomorrow we will be doing a lab on this type of stuff, so if you were not here today, you can pick that up just fine and do some lab tomorrow. You're also going to talk about our project for this unit in class today, so if you were not here, you're going to want to get the notes and the different rubric and outlines for this assignment. And tonight, you're going to try some practice problems, so number 1 and 2 under lesson 4. Go ahead and give this a try. Let me know if you have any questions.